Okay, so first thing I want to look at are the parent functions. So I have characteristics filled in for you guys, and I'm going to highlight the main things that you want to have written down. So parent functions, remember, are important to us because they start us with the most basic thing that we should know about the function. Okay. These a little bit bigger. Okay, so first thing. If I touch this, is it going to move it or is it going to write? It's just going to move it. I want to write. Your quadratic should have these points. Okay, if you can't see those points, another way that we look at them is through a table. And the tables are going to be really important for us because they're going to kind of provide us a shortcut. Since a point is graphed by going an x distance and a y distance, when we do our transformations, our x distance is being shifted and our y distance is being shifted. So if we have these parent function tables memorized, then we should be able to do the transformations faster. So the points that you centered around 0, 0 because that's the vertex. And then we had, so basically these 5 numbers, which we often see in our parent functions as things we plug in for things that are centered around 0, 0. Okay? And if you forget the parent function table, you should be able to quickly get it by just doing what the parent function does. And in this case, our parent function squares things. So -2 squared should be 4, -1 squared should be 1, 1 squared should be 1, and 2 squared should be 4. These are the points that I have plotted up there to draw that quadratic. Okay? So then just a review of some of the characteristics of this. So the h and the k should give you your vertex point of your quadratic. So your h and k should be 0, 0. And because this graph hits at 0, 0, both our x-intercept and our y-intercept are 0, 0. Okay, so x-intercept, y-intercept, vertex, or hk are all 0, 0. The domain for the function, remember, is your x's. You can plug in x values. Okay, so all. Notice that with our graph, we continue upward, but this vertex point is our absolute minimum of our graph. So our range is only at 0 and above. So our range was y is greater than or equal to 0 or from 0 to infinity. Okay, any questions about intercepts, vertex, domain, or range, just for the parent function? All right, how many of you guys remember increasing and decreasing intervals? Okay, a little bit. Okay, so you kind of have to do 2 things with those. So I'm just going to point this out to remind you. When we look at the graph, we read it from left to right, like we're reading the page of a book. When you read this graph, if you were on this parabola, as you moved from left to right, the first thing that would be happening to you is you'd be going downhill, right, if I'm moving across the graph this way. Then you'd hit the vertex point of the parabola, and then as you continued to move across the graph, you would now be going uphill. So this part where you were would be the decreasing part, and then the part where it changed to where you were going uphill would be the increasing part. But here's the weird part about how we write it. We don't write it as, oh, I'm going up to here or down to here. We don't write it as vertical stuff at all. We actually write it according to the domain, the x's that have to do with the increasing and decreasing interval. So the graph was decreasing, then it hits some point where it changes, and then it was increasing. That point where it changed is 0 on the x-axis. So what you're going to tell somebody when you list the increasing and decreasing intervals is you're saying, for all the x's on this side of 0, my graph, where for so the decreasing stuff is happening on this side of 0, and the increasing stuff is happening on this side of 0. So when they say increasing interval, you think not about where the graph is going, but you think instead increasing happened for these x's. That's from 0 to infinity. Okay? The decreasing interval was on this side of the x value of 0. So it's from negative infinity until 0. Tricky because we think up and down when we think increasing and decreasing. We do want to look at what the graph's doing, but when you list it, you're listing the domain or the x values that go with it. Okay? All right. Rate of change is not something important to us in this situation, and neither are asymptotes. So those of you that don't have a note guide, you don't even have to write those down. Those of you that have it, those are totally not applicable in this situation. Okay, 1-to-1. Do you guys remember what 1-to-1 is? Okay, Summer? Yeah, both ways. Yeah. So you guys know the vertical line test, how you test if something's a function? Okay. In order to be 1-to-1, it has to be like the function and an inverse of that. So not only does it have to pass the vertical line test, where you have 1y for every x, but it also has to be able to pass the horizontal line test, where if we test the y's, they only have one x that goes with them as well. So this fails the horizontal line test up here, which is why it's not 1-to-1. So that's just a yes or no statement. You're stating yes, it's 1-to-1 or no. Our axis of symmetry should be at x equals 0. It's important when you write an axis of symmetry or an asymptote that you write it like a line. It's not a number. It's an equation of something because we need to know which direction it's going on the graph. And then every quadratic has either a maximum or a minimum. Okay, this one in this case, this vertex point would be considered a minimum. So maximum value is none. Minimum value, because they wrote the word value here, they're really just looking for the y coordinate of the vertex, and then that's why we just listed the number 0. And that one's just a single value. So I know we're going a little quickly through these. These are all like, we should have done all of these functions with this same exact format in Algebra 2. We might need a little refresher, but they existed. Okay? And then we're going to look at your cubic function. Really, our emphasis in this course, we're going to be doing domain, range, and intercept finding and graphing with transformations. So it's really important that we know the parent function and the shape of the graph. Okay? So let's look at your cubic function. So in case you forgot, but you saw it on the cheat sheet when we were working on the creature project, our cubic function, okay, is a lot more narrow. Here are the points I have marked on this. I'll explain which ones they are in a minute. So the cubic function grows faster because you're cubing things. That's why it looks more narrow. And it doesn't turn around because when you cube things, negatives can still turn negative, positives can still turn positive. It's still centered around 0, 0. So our parent function chart has that same kind of starting vertex-ish point, even though it's not really a vertex here, and we still used numbers around that. The difference in this case is that we cubed the numbers. So 2 cubed ends up being 8, 1 cubed is 1, negative 1 cubed is negative 1, and negative 2 cubed is negative 8. So these points are how we're doing this structure. Okay? So again, our goal today is to make sure we understand shape when we see a cube versus a square, and that we know which one of these parent function charts goes with it. Okay? So again, all the intercepts and like the HK value, 0, 0. Okay, because it's just the parent function. We haven't moved it over. They're all 0, 0. Okay? So 0, 0 for each intercept and the H and K value. Domain and range for this function. So you can still plug anything in and cube it, but you can also get anything now. You can get positive numbers, negative numbers, everything, okay? So now the domain and the range are both all reals. Okay? You don't have that turning point like a quadratic. You don't have a place where it stops going up or down. Okay? It just continues in both directions. is not written well. Okay, so now if we're reading the graph from left to right, if you were on this graph and you were moving from left to right, the whole time you would be following the function as you go from left to right, you would just be going up. Does everybody see that? That the whole time, sometimes it's flatter, sometimes it's steeper, but the whole time if you're going across this way, you're going up. That means there's no decreasing interval. There's no time where you're moving across the graph from left to right where you would be sliding down the function. You would always be climbing up the function. So no decreasing interval. Our increasing interval then is the entire thing. So from negative infinity to positive infinity, the entire domain of it. Okay. And again, rate of change and asymptotes don't matter in this function, so you can cross them out if you have the note guide. If you don't have the note guide, you don't have to worry about those. Okay. Our one-to-one, is this function one-to-one? So this one passes the vertical line test and the horizontal line test because it doesn't turn around and violate any of those rules. So this time, have an axis of symmetry. There's some symmetry there, like rotational symmetry or something like this, but nothing that we're going to call an axis of symmetry. And no maximum and no minimum value, just none for each of them. Because it continues in both directions, we can't establish any bottom or top point, okay? Is everybody okay with just a reminder of kind of how these functions worked, okay? We really want to stick in our mind the shape and the parent function table because that's how we're going to get graphs when we change it from being the super basic parent function, okay? All right, so that's what we're going to try and do next. We're going to try and graph a quadratic and graph a cubic that have some transformations in them and are not just the most basic parent function. Okay? Any questions about this before we leave this idea? Some people are still writing, so I'm going to give you guys like a couple minutes. If you had a question, I'm going to walk through. Okay. So we're now going to graph something that's more complicated, but the reason we had to review the parent functions is because we probably needed a little refresher, maybe even more from Algebra 2, so we're going to keep doing that. This problem, the problem that's up there is something you could have totally done in Algebra 2, okay? It doesn't have any of our new transformations. There's no horizontal, stretching, compressing, or reflecting, okay? But like I said, we might need some reminders. So look at where the numbers are in the equation and remember what transformations those do. So we did that little investigation last week too to remind you about A and B and H and K and how they might adjust your graph. So right now you have an A value of 2, an H value of 5, and a K value of -4. Is that okay with everybody in that equation? That our A is 2, our H is actually +5 because the general equation is built with a minus sign already in that part. And our K value is -4. Okay? What kind of transformations do these cause? Okay? If the A value is 2, what's happening to our graph? Stretching which direction? Vertical. If it's not happening to X, it's not horizontal. So it says if it's not happening inside of this little squared thing, only the horizontal stuff happens in here. Everything outside of the squared is vertical stuff. So this 2 is a vertical stretch. On our graph, we measure our vertical distances with our Y coordinate, right? So our Y stretched by 2. What that means is if I was 3 up before, now I'm 3 times 2, which is 6 up. Basically, every distance is getting doubled. So we can just do a calculation and double the Y distance to get the new Y. The other vertical thing right here is that K is -4. And what does that do to our graph? Shift it down 4, right? If you want to move something down 4 on the graph, then whatever it sits at, that Y value needs to be subtracted by 4 to move it down 4 on the graph. So that thing happens. So if I double the Y coordinates and subtract 4, I'm stretching them and moving them down 4 on the graph. But I can do it through arithmetic and just do a little bit of calculation. Okay? There are separate things happening horizontally. Inside of here horizontally, we have this X -5. That means that H is actually a +5. Okay? what's happening to my graph here? What does h cause the graph to do? Yeah, left or right, right? Which direction are we going in this case? Right 5. Okay? That's why they wrote the formula super weird and you have to take the opposite of it, so that when you find h is positive 5, you actually know that it's moving to the right 5. If you want to move points to the right 5 on a graph, you need to take whatever x they're currently at and you need to add 5 to it to move it over 5 points. So we're going to take our x and we're going to add 5. This can make our new table, but it does have to be a quadratic. So if we want to just do this arithmetic, we have to start with the parent function that you guys have on the other page. So this is why knowing the parent function is really important. You guys have it right on the other page, so you guys can look at it. I can't see my other page, so I had to rewrite it. So this already does the squaring. If I can just now take all the x's and move them to the right 5, so I just want to take the x's and add 5. And then to the y's, I want to vertically stretch them and move them down 4. Then the y's, I'm going to do these things too. So I'm going to take every x value right here. I'm going to take it and add 5 to it. So negative 2 plus 5 gives me 3. Negative 1 plus 5, 4. 0 plus 5, 1 plus 5, and 2 plus 5. Is everybody okay with why my x list now says 3, 4, 5, 6, 7? Do you understand what I did? I took something I already knew and had plugged in for the x's, and I transformed them. Summer? Yeah, I'll explain to you my expectation in a minute. So this is a different perspective. You can do it this way or a different way, and then I'll tell you what I need from you, and if your other way works fine to get me each thing I need, then you're totally good. What I ran into last year is that people were making tables of points that weren't actually the points of their graph because they didn't fully understood what they did last year. Some people were okay and some people weren't, so you guys can decide. So then I'm going to shift all the y's by multiplying them by 2 and subtracting 4. So 4 times 2 would be 8. Minus 4 is 4. 1 times 2 is 2. Minus 4 is negative 2. 2 times 0 is 0. Minus 4 is negative 4. 2 times 1 is 2. Minus 4, negative 2. And 8 minus 4 is 4. Okay. I now have a new set of points, and there should be some things here that stand out to you as making sense. First of all, we still kept the symmetry of our parabola, right? Like, we still have the copied y values on each side of the vertex. Do I still see my h and k as the vertex? H was 5 and k was negative 4, and there's my vertex. Okay? So to get back to Summer's question about can you do it a different way, totally. Here's what I'm going to ask you for on a test. Can you list the transformations? So can you say things like vertical stretch, shifting right 5, shifting down 4? Okay. Can you graph the correct function for me? So we're about to put the points on there in a minute. And can you list for me a table of points? Now, you don't have to have made the table the way I did. You can get your points first and then make the table. But I want you to identify for me the 5 points that you graphed, graph them, and be able to tell me the transformations. So if you can do all those things, and then domain and range and intercepts, but we'll talk about those in a minute, okay? So I'm going to go ahead and put these on the graph. So there's my quadratic. And do a couple of quick checks. Are your h and k making your vertex? Is it in the right spot? Is it facing the right direction? Should it be facing up? Does it make sense that our parabola is facing up? Yeah. There was no negative a value to flip it over, so it makes sense. And then kind of look at its shape. It's a little skinnier than our normal parabola, like more narrow, but that makes sense because we had that like vertical stretching thing going on. Okay? Is this okay with everybody? Okay. Now, our x and y intercepts, we're going to come back later, but things that you should be able to recognize here, your h and k, we've already talked about them a lot. They should match what's going on there. And I'm not going to ask you to fill out this chart every time like we did in Algebra 2. It's important for you guys to know these things. But again, our focus is going to be on, can we get the graph with the transformation? So can we list some points, have a graph, and know how to label the transformations and find intercepts because we're bringing in a new transformation. Okay. What would our we'll go back to intercepts. We're going to solve for the intercepts later. What would the domain be for this function? Chloe? Yeah, negative infinity to positive infinity or all reals if you guys like to use that notation. Okay? You can plug in anything. Somebody else, give me the range for the function. So when you look at this function, what is its range? Sam? Good. So she said negative, looking up and down. Smallest is -4, but it can go up forever. So from -4 to infinity, or y is greater than or equal to -4. Okay. Who thinks they can give me the increasing interval? Chloe already gave me one. Genevieve. So you're right that we're going to the right. So here's where it turns around, right? So this side of the graph is where if I was moving across, I'd be increasing. So this is the increasing part, but not 0. It lines up with 5 on the x-axis, so from 5 to infinity instead of 0. So our increasing interval is from 5 to infinity. What would our decreasing interval be? Somebody else. Yes, Connor. Good job. Negative infinity to 5. All right, somebody else. Is this function 1-to-1? No. Okay. All the quadratics are going to fail that idea, right? We don't need rate of change. Somebody else. What is my axis of symmetry? Sam already gave us something. Genevieve already gave us something. Yeah, Jeremy. Good. X equals 5. Okay. Somebody else. Our minimum value. Yeah. Good. -4. So we do have a minimum, and the value that goes with that, just the y value, is -4. What is our maximum value? None. Okay, there isn't one. We don't have to deal with these. Okay. Questions on how to transform. So this is one way. Summer was just telling you guys about, she knows how to find the vertex, and then she does other things to get the graph. That's totally fine. Honestly, if you know the vertex, you could even plug in points around the vertex and get the graph. I just want to make sure you guys can get the graph in the right spot and you have a table of values to help you. If you're proficient in another way before this, I'm never going to take something away from you. I'm never going to make you use my method. I'm just going to give you other methods you can use in case you struggled or in case you like them better. Okay? Is this okay with everybody as far as getting a graph? So you could look at this equation. You could get a table of values in a graph in whichever order you do that or how you do that. And you could say vertical stretch, shift to the right 5, and shift down 4. Okay? And give me the domain and the range. All right? Okay, we're going to try one with a cubic as well. This one will be a little more difficult because it's going to incorporate the new portion that we're looking at, that B value. What if there's something that's causing horizontal stretching and compressing? Okay? So the last graph that we're going to do today is going to be a cubic. I'm actually going to make the graph like that. You can see the equation up there, and we'll deal with it in a minute. Okay, so why the cubic is different, it might be different than what you've done before depending on your experience, is that now there's a 2 in here. So we didn't have to deal with that before. That was not something in Algebra 2 we had to deal with. But we saw in our investigation that that value acted a lot like our A value. It caused stretching and compressing. We took a little bit of summary notes on what exactly it does. Okay? But we also have to deal with our B separate than our H. So if you guys look at this equation right now, what do you feel like the value of H is? I look at the equation. What does it seem like H is going to be? -6. But in your investigation, you tried, and those of you that tried the 6, it was too far over, right? It actually had to end up being 3 because what we had to do is we had to rewrite this function that the 2 was kind of separate, not really separate, like we're not taking it way out and moving it or anything, but we're just factoring it out of the x minus h because we've only studied h when it's just like x minus h. We've never studied it with like a 2 in front of it, so we have to separate the 2 from it. When we do that, what's left inside of these inner set of parentheses? It was 2x plus 6. Now it's going to be 2 times what? X plus 3. Okay? The 2 is still inside the cubing, but it's separated from the little x minus h group that we were looking at. Okay? So let's talk about vertical first, because the vertical is not changed. Everything you know from before. Okay? What is this going to do out here? What kind of transformation does putting a negative here cause? Reflection, okay? And it changes the y, but when you change the y, it makes it reflect over the x-axis. So this is a reflection over the x-axis, but it's changing the y. The only things that can change the x are inside of the cube with x. Everything else is affecting the y, the stuff after it's cubed. So our y's are going to get their opposite, okay, sign than they had before, which is going to flip them over. And then they still have this shift over here, which is going to shift them down 4. Is everybody okay with our vertical transformations? Same idea as what we were using with the quadratic, and same idea as what you've done in Algebra 2. Part of the horizontal stuff is going to seem the same. This is what's going to cause us to have to think a little bit harder than we might have had to before. Okay? Now that you've factored it, you at least have a really clear x minus h package right here. Okay, what is our h value? Our h value is negative 3. Okay, so what kind of transformation is happening to our graph? Shifting left 3, right? I get that it says x plus 3, but we've done all these investigations. We studied this last year. We understand that now means h is negative 3, and it's shifting us to the left 3. So whatever happens to our x coordinates to get shifted to the left 3, we're going to have to subtract 3. Okay? Everything so far that we've written up there is really similar to what we just did. This 2 is the only thing that's different. Okay? So we talked a little bit about this yesterday, and it's a little strange. The 2 means that it's going kind of twice as fast as it used to. But that's not what we measure on the graph, okay? If you're going twice as fast as you used to, let's say you did your homework twice as fast, okay? How much time did it take you to do your homework compared to normal? Half as much. And that's kind of the relationship that we see here. If x is reaching a y value twice as fast, it only takes it half as long to get there. And that's what we're measuring. So this says 2, okay, b is 2. That really means you're going to use a half, okay? And if you're multiplying things by a half, are you making them smaller or bigger? Smaller. So you're really doing a horizontal compression, okay? But we don't know how to label that, or it's a little more difficult until we think about this. So pull out b every time, is my advice, if you're unfamiliar with this. But write down what you're going to use, and then that will help you identify 2 things. One, it will help you to know what to put here, that the distances are getting half as much. And 2, it will help you name it. I now know that multiplying by a half is making things smaller, so I now understand why it would be called a horizontal compression instead of a stretch, because my eyes see the 2 and they immediately want to say like the opposite of that. But I want to make sure I do it correctly. Okay? And so now we're going to go through and transform the cubic points this way. And again, we have to start with that parent function. So we're going to take each of the x values and transform them by multiplying by a half and then subtracting 3. Now, a lot of you guys might not like the work with fractions, but it's going to happen, especially if we're doing horizontal stretches and compressions. If you struggle with it, write out what you're doing on the side of your paper and just do all the fraction operations like you would when you first learned how to do fractions. Most of you are efficient at it that way. You just feel like you shouldn't have to do that, and you try to do it faster, and then like it doesn't work that way. So my advice would just be to write it out. So negative 2 times 1/2 minus 3. So if I have to, I'm doing this kind of thing. Negative 2 times a half minus 3. That's negative 1 minus 3, which is negative 4. Okay. And then I'm going to go through and do that with each different value that I have here. So the next value is negative 1. Try again. So I'm doing the amount of work that you guys would do if you're uncomfortable with fractions. So negative 1 times a half minus 3. So that's negative a half minus 3. I'm totally good with you guys then just writing that's negative 3 and a half. Graph and write fractions in their improper form because that's easier to do like the math with them. But if you're just graphing, negative 3 and a half is okay for that purpose. Okay. 0 is not too hard. 1/2 times 0 is 0. Minus 3 would be negative 3. And now I'm going to go and do the positive values. This is where you need to be a little careful. When you plug in positive 1, if this is positive 1 times a half minus 3, that's positive half minus 3. That is no longer negative 3 and a half. What is that? So you either have number sense where you're like a positive 1/2 and a negative 3 make. Okay, so if you don't know, then you should be making common denominators, and you should be thinking of this as like 6 over 2. So positive 1 plus negative 6 is going to be negative 5 over 2. Okay. And you can either as negative 5 over 2, or you can divide it out so you can get it. So you guys have to be okay with fractions. But I'm not going to stand up here and lecture you. I'll help you individually for the people that really struggle with fractions. But I mean, basic, if we have to go back, we make common denominators and all that kind of stuff if you're struggling with the fraction arithmetic, okay? And then 2 times a half would be 1, so that works out a little bit better, and 1 minus 3 will be negative 2. Okay? And then we would go through and do the same thing for the y, so change their sign and then subtract 4. So this will turn into positive 8, and then I'll subtract 4. This will turn into positive 1, and then I'll subtract 4. 0 minus 4, negative 1, and negative 8 minus 4. And I now have a new set of points to graph. And again, H and K should show up in that point that's like your vertex point. Does it make sense that 0, 0 turned into negative 3, negative 4? Okay, my H is negative 3 and my K is negative 4. That's where my graph should be centered around. Okay? So negative 3, negative 4, and then I'm going to graph these other things around it. So negative 3 and a half, negative 3, negative 4, positive 4, and then negative 2 and a half, negative 5, and then negative 2, negative 12 is somewhere down here off my graph. Okay. So then look at it. Does it look right? Does it look like a cubic? Okay. It does. It looks skinnier, but that's from that horizontal compression, and it looks like it's kind of the wrong direction, but that's from the reflection that we had going on there. Okay. So the biggest things of importance to us here are that you can identify the H and K, because that will help you know if your graph seems significantly correct. And then X and Y intercepts we're going to work on solving tomorrow in our little 20-minute period. It won't take that long. And then domain and range for a cubic. What are our domain and range all the time for a cubic? All real numbers. Okay, they go left and right. They go up and down. So that part shouldn't be too bad. Okay. And then remember, these don't have maximums or minimums or axis of symmetry. Okay. This one is completely decreasing. Right? Because from left to right, it would be going down. So the entire time, it's decreasing. It's not increasing at all. No maximums or minimums. No axis of symmetry, rate of change, asymptotes. But it is 1-to-1. It does pass those tests.